Good morning. So I would just like to give you a short presentation on additive manufacturing and composite materials. Just to give you a bit of background on this presentation, it was something to do with some internal communication we wanted to highlight within the agency. To make you aware of this evolving technology that's changing the industry, as you can imagine, and as you are experiencing. And to show that we're keeping up to pace with everything that's happening in this domain. So what we've done is basically I've reviewed about 30 presentations on additive manufacturing. There's been a few workshops on this, and tried to boil it down to 9 slides, which I'm going to present to you right now. And Wolfgang is going to present 2 of those slides on a more technical aspect. So here I wanted to show you.
You can look at.
Sorry.
You can look at also there.
Okay.
Maybe
I didn't know. Thank you. So first of all, the definition of additive manufacturing. So as you can imagine, it's adding layer upon layer as opposed to removing from a solid block, which was the milling method. So you've got 2 different types: the laser melting and the photopolymer jetting. One is used for metallics and one for non-metallics. We're using this in many, many applications, as you know: airframes, engines, systems, cabin interiors, and modifications and repairs. Just a few figures that were coming from Airbus. They expect to have around about 3,000 proprietary parts, meaning spare parts, up until 2025, which will be made using additive manufacturing. Same thing up to 260 proprietary tools up to 2025, and there's about 200 projects that's specific for customized for airlines. Next slide I wanted to show you is to present you the future benefits and the present benefits of additive manufacturing. So first of all, fast prototyping, acceleration of production time, meaning you can develop and you can print a part. An engineer just takes the design, can take 1 hour, and then just prints it in 1 hour. It's easily done. Very soon we will see more than 1 laser working to do the laser printing. Up for the moment we have up to 4 lasers working, but we have a problem there related to spatter, which stops us at 4 lasers for the moment, but they might develop this even further. Reduce part counts. The best example is the fuel nozzle, which was before 20 parts and now is just 1 part. This was quite complex complex parts before in the previous time. This is of course lighter, it's fuel efficiency, and next one is, I thought, a very good example also of a turbine frame, just to show you how it reduces the workforce also, whereby you needed 60 engineers before. You only need 7 now, whereby you had 50 manufacturing sources, you only have 1 now, where you had 300 parts, only 1, and where you had 5 repair sources, you only have 1. So this is a very good example of this evolving technology. Then it has also an environmental benefits. Of course, parts are lighter, so fuel efficiency, of course, comes into that. And also, the old system of milling generated 95% of waste. Don't have this anymore. The energy produced for removing the material, etc., the transportation, and the fact that you can build everything in-house as long as you have the printer. And then, of course, optimized design. You've got an efficient design, weight saving, and there you've got the bionic structures, which is there, which is one good example. Then what we want to say also is on composite materials is it's very much used in the general aviation and rotorcraft industry. Some examples are propellers, the fan blades, the seats, the undercarriage, and there's more to come. Then we wanted to keep you also aware of research and development. The agency is working on this. Materials and research and development, the key themes are damage modes, manufacturing defects, statistic strategy, test analysis pyramids, which is very much used, modeling and simulation methods. Here we've got 2 projects. You can go on the internet and find out more. You've got the Clean Sky and the Horizon 2000. What I just wanted to say for Clean Sky is they had in total 18 Clean Sky projects for 40 entities, basically working on additive manufacturing. And for the Horizon 2000, they have 5 additive manufacturing projects where they're looking at the powders, the simulation methods, the validation processes of the machines, etc. And they have quite important budgets there, 20 million out of a total of 250 million for aviation. The next slide I will leave to my colleague.
Okay, thanks, Philip. So, welcome. My name is Wolfgang Kaufmann, structures expert in the large aircraft department here at EASA. So, I will proceed with the disruptive technologies, which are really the additive manufacturing, and since a much longer time already the composite materials. And what is the characteristic with this disruptive technologies? It's material and processes which are changing. So for the composites, we have it since 20, 30 years, because aircraft manufacturers started to install aircraft parts in composite, for example, rudders or whatever. So it happened 35 years ago already. But now we are that far that there's a complete composite aircraft flying around. This is the Boeing 787, the representative for this. So that means the step was made with the initially very new material and a lot of unknown things, and the gathered experience that we finally have a full, let's say, plastic aircraft. It shouldn't say something negative. Huh? Now we have the additive manufacturing. You could say composite is possibly, well, similar to additive manufacturing, because you just add those materials which you need. You don't manufacture something from the block. That means with a lot of shipping and debris, which you have to recycle, and high costs involved for this. So the main thing with this material and process changes is that you have engineering properties which are depending upon those things like material and process. That means for built-in into parts or repairs. And that requires appropriate interaction between DOAs, POAs, maintenance, and material suppliers more than before, because processes are more sophisticated, can do more mistakes, which may have more effect on safety finally. So we have to have lots of points, well-trained staff, and so on. So the impact for the regulators, not only EASA, but also FAA and Transport Canada, here sitting in front, they have the same problem. And the same impact. The impact is, so we have rapid product application development, increasingly safety critical applications for additive manufacturing and composites. So that means TCH and STC holders, they come towards us and say, well, we would like to manufacture new parts with this new technology, and we would like to certify this. So we mainly used to say, well, we don't certify parts or, let's say, materials and processes. This is something which you have to do while you have to work according existing standards, which are currently being worked out for this kind of things, for additive manufacturing. For composite, they are already existing, but they are always improved, of course. Well, what else? Changing a relationship between design, production, and continued airworthiness activities is existing. So they are more entangled than before, because things are more sophisticated. The design allowables are depending on the process parameters and the material change. And you have anisotropic material, and this has to be figured out. We have to work out what is the effect on our final material properties. So that comes back to DOA, POA interface, DOA Part 145 interface. They all have an impact upon design allowables. Everything becomes a bit more complicated, and so the manufacturing process and the material itself, and we have to take care of it with specific means. So what else? We have to have an understanding of the impact upon engineering properties. That means competing damage modes, for example. We have to have an understanding of the test analysis pyramid. Can we use it as we've used it before for metallic materials? doing lots of coupon tests, and then going up to finally component tests? Or do we have to do more component tests or sub-component tests for those new manufactured materials until we have a certain confidence in the quality? Yeah, we have to understand the manufacturing defects, sensitivity to key parameters, machine parameters, raw material production and handling. And due to this, we have one very important slide here. This is coming from the laser powder bed fusion. So that is metallic powder, which is being melted by laser from additive manufacturing. This is one method. And the first thing you have to do when you have such a machine, you have to figure out, so what is the operation window where I get quite decent and solid material properties? And you actually have to vary laser power and scanning speed. And you see you have to, well, if you're too fast with the scanning speed, you will have a lack of fusion, of course. And if you are too high with the laser energy and too slow with the scanning speed, you will have to, on the other hand, well, other effects which make erroneous material there. So, and finally, you get really an operational window which is in this triangle, somewhere in the middle. And this is something which you have to check out, which you can't just take from the machine manufacturer. So you really have to check out under your environmental conditions if your machine is doing the same. So find out the right operational window. This is what we've learned recently at the authorities. So we had the opportunity to have a training on this. And this is a very important thing. Then already mentioned by Philip, statistical strategy. What does it mean? So it means mainly handling the paragraph 25613 to produce material A and B values. And there's a question, do we have to have thousands of material probes or do we have to have just hundreds of them or even less? It's depending possibly on the parts we are going to produce, if it's critical or non-critical. So all these kind of things have to be figured out. And okay, we have increased use of shared database, of course. For the composite materials, we have the NCAM process. We have CM on this. This is a CM, what is it? -S-004. So there you can read something specifically on this process for composite materials and the shared databases. And yeah, the next one is training. I've mentioned this already, not only for the industry, also for the regulators, because we have to be in the loop to be able to draw decisions to produce guidance material for others. And what else do we have to do? We have to ask the question if process control monitoring replaces inspections. And what I have already mentioned, we have to consider if there's a need to change rules and guidance material. And to do a performance-based regulation. That means for non-critical parts, possibly just doing less substantiation, or for critical parts, doing the full requirements. So this kind of things we have to figure out, and we try to develop some guidance material for you. And yeah, so I don't want to go on to the other points, so it would take too much time. Okay, we still have something. I would like to come to the next slide. This is our EASA additive manufacturing strategy. It's being worked out in the EASA AM working group. We have subject contacts as identified also in our third memo for additive manufacturing, the CMS008. So all contacts points are listed there. So whenever it deals about airframe structures and printing of materials, you can approach me or our senior expert Simon Wade. If it goes about propulsion, for example, the fuel nozzle, which we've seen, you just contact Omiros. And for cabin safety, Thomas Onimus, and so forth. So you can really rely on this list of contact points. Just involve us as early as possible. This is one of the most important information which comes out also of the existing CM on additive manufacturing. You see down there the link. It's in the presentation not active. You have just to copy it and then to find it. Or you just Google, just put in EASA CM S008 and then you get it. So just a last slide on the composite material to show you that it's not that much different from the other additive manufacturing method which I've shown to you. So what is the definition of composite material? It's a combination of two or more materials and differing in form or composition, and they have a clear interface. So you have layer per layer and you have different orientation in the layers, anisotropy. This is very much, very well known from the composite side. And you have here a quite good slide where you can see that the anisotropy of the composite material varies in strength with the orientation of the layers. And yeah, so we have mainly polymer matrix composites, ceramic matrix composites, we have metallic matrix composites, sandwich structures, bonded structures. This is what we have, and here as well the design challenges. Engineering properties are dependent upon material and process. We have an anisotropy, as already mentioned. Properties vary with load application direction. We have competing damage modes. Some of them are difficult to detect, so we have to find possibly more sophisticated and powerful NDI methods. And we have the environmental sensitivity, of course, due to radiation, moisture, and all this kind of stuff. And also for the composite materials, EASA has got a strategy, and this is called Composite Materials Safety Strategy, CMSS. We have there mainly two objectives. The CMSS1 is to identify and act upon high-level, internationally recognized common safety themes in conjunction with other regulators and industry. That means so we are harmonizing all this kind of stuff with FAA, with Transport Canada. They do the same. And then the second objective is, well, to prioritize and act upon safety themes of more specific interest to European regulators and industry. That means sandwich structures, for example, composite seat testing, composite STCs, extending the AFF, HFF shared database. And this is mainly everything what I would like to mention. So we have a strategy on composite materials, on additive manufacturing, and please look up the relevant CMs on that on our website. So it's your turn.
So I'll speed up, so I suppose you have some questions after that. So these two following slides are because we're presenting some material here in the agency on the first floor. You'll be able to go and see some parts which you can touch, which we received from Airbus. Very soon we'll have some parts from Rolls-Royce and Safran. So this is just to show you a little bit of history on the composite materials. So you have wood and fabric for the Lindenthal. You have the Juncker J1 that was metallic, duralumin. You have sandwich material, bonded plas, balspa, and polywood. And now what's coming very soon, or it's already there, sorry, is the A320 empennage, the fuselage of the Boeing 787 and the A350, and the glare crown on the 380. And before you had the wing box on the ITR. And then the next slide is just to show you the effect of composite materials on the aircraft. So, as I said, it was engine, system, cabin interiors, modification and repairs. Here you can see clearly the carbon fiber reinforced plastics on the aircraft, monolithic and sandwich, quartz glass, what's used on the aircraft. All this is presented for you on the first floor, if you can see the slides there, and some material which you can touch, which are here on display. So please go and have a look on the first floor. So if you have any questions,
Well, you could have many questions because the topic is very interesting. And thank you so much, Wolfgang. And Wolfgang, I didn't have the possibility to introduce. I just said he's an EASA expert for structure, but he's actually really the focal at agency level and the organizer of the AM workshop in EASA. So thank you very much.
Focus for airframe materials.
For additive, additive manufacturing. Yes. And together with all the others. And thank you again, Philippe. Maybe we may just read some queries, and we promise to come back to you in a proper way after discussion also with the people, because we need to go on. And I saw already the next speaker ready to come. So, do you want just to mention
I can just mention one question. Is there a CRE related to additive manufacturing, Wolfgang? Yes, no?
No, there's no CRE. There's our CM as a guidance because, well, the top level requirements are not really changing. So we just want to focus on specific of those specific requirements of those, where there's much more to do than for other requirements. For example, the 613 requirement for the statistical A and B values, and very important is also that the the information transfer from DOA to POA and from DOA to 145 due to additive manufacturing, that means subcontracting and transferring parameters for process parameters and material parameters for the machine. This is very important, where they have to focus on. And this is mentioned in the CM, so we don't need a CRE currently. So
thank you very much. I think we can go to the next